Today we are here to deduce the Lorentz transformation equations that we generally use in studying modern physics, quantum mechanics, and things like that. So first of all, we consider two frames of references. One can be said to be, let's say, frame S with the y, x, and z axes represented by this, and another frame of reference that we will later say to be S prime. This is the x prime, z prime, and y prime axes. Now, when we consider these two frames of references, we consider that S prime over here, this is moving in the x-axis, only in the x-axis with respect to S at a velocity of v. So if we take any arbitrary point in the S prime plane, let's say point P, the coordinates will be x prime, y prime, and this is z prime. Now see, by intuition, we could say that this length itself is x prime. So we could also say that from the frame of reference S, this entire distance is x. Okay, taking this into consideration, we can now start deducing the Lorentz transformation equations. Now, from the Galilean transformation equations, we could say that from the time of reference that is considered from frame of reference S, this entire distance of x, starting at time t equals 0, x can be considered to be c times t, and this is from Galilean transformation equations. And then again, from the frame of reference S prime, we could say that x prime over here is equal to c t prime, equation 2. Now, we could also say from these two figures that x prime from the frame of reference of S can be said to be, and similarly, we could say that x is equal to x prime plus v t prime from the frame of reference of S prime over here. Now, when deducing the Lorentz transformation equations, we assume that in the Lorentz transformation world, the new equations will be related to the Galilean transformation equations by a factor of a constant that we will term as k. Now, so taking these into consideration, that factor k can be written down as equation 3 and 4 by x prime is equal to k, x minus vt, and x is equal to k, x prime plus v t prime. This will be our equation 5 and equation 6. Now, it is not hard to understand that k in and itself is only dependent on the velocity at which this frame of reference S prime is moving away from the frame of reference S. So we say that k depends only on v and not on x or t. Alright, so we have equation 5 and 6. Using equation 6, we can play around a bit and find the value of t prime. So we combine 5 and 6 and we find a value of t prime using the following mathematics and algebra. So we have x is equal to k, x prime plus v t prime using equation 6. And then again, equation 5 gives us one representation of x prime, right? So we could further write this down as, and this is using equation 5. And we further simplify this to get, and now we represent t prime with respect to the other variables. This is our equation 7. Now, we also know that using equation 2 2 over here, x prime is equal to c t prime. So if we plug in the value of t prime in x prime is equal to say c t prime, we can further get a value for x, if that is we use equation 5 over here to substitute that into x prime. So we get that x prime is equal to c times, and x prime is basically, and with further algebra we get that now we can represent x with in terms of the other variables over here, and we do so, and we get that x is equal to, this is our equation 8. A lot of equations so far. Now, if we use equation 1, that is equation 1 over here, and back substitute the value of x over here, then we can find a value of k squared that can be used to find our required Lorentz transformation equations. So equation 1 says that x is equal to ct, and now if we back substitute the value of x over here, then we get that, using further algebra, we can say that this is now this equation is achieved by taking all the terms to the left side that has k squared in them. Now, by further simplification, we can get that this equation over here that is above can be set to be this. And as you can see over here, these TC's, they cancel each other off, and we could say that k squared is basically minus c squared t over v squared t minus c squared t. And using some further simplification, we can cancel these t's off as they are common factors, and we could write k squared as negative c squared over v squared minus c squared, and then we can take the c squared in the denominator, and we have that this is basically v squared over c squared minus c squared over c squared, and this is negative 1 over v squared over c squared minus 1, but we generally don't like to have negatives in the denominator. So what we do is we multiply the denominator of the numerator with a negative 1, and we get that this is 1 minus v squared over c squared, but if we take the square root, then we get that k is this 1 over the square root of v squared over c squared, and this is the value of the constant k. Now things are much easier from this point. What we now do is we plug in the value of k in the other equations that we have, beginning with x prime is equal to k, x minus vt. Plug in our values, and we get that x prime is basically x minus vt over 1 minus v squared over c squared. Now, since our velocity is only occurring in the x-axis, y prime and z prime, they remain the same as y and z. It can be different if the velocity is being occurred in the y-axis or z-axis, but since we're just dealing with the x-axis over here, it's the case over here as shown. And similarly, if we plug the value of k into equation 7, we get that well, that's all.